vertices S and T, the graph being weighted with non-negative edge weights, given algorithm so that we can find out the shortest path from S to T. Remember, uh, in this problem, we say single source shortest path. Why this is the name? Because if we run the algorithm, then essentially if we vary this T, we can find out. I mean, from this S, the algorithm is such that from this S, I can effectively find out the shortest path from S to any vertex in the graph. Okay. So that's why this is called the single source shortest path problem. Okay. And famously, this is often known as Dijkstra's single source shortest path problem. Dijkstra's problem. So how this problem is solved? Okay. So let me just solve it here itself. So as you see, so initially what happens, this S is assumed to be at a distance of 0 from itself, and all the other nodes are at a distance of infinity. Okay, at a distance of positive infinity. Okay, like that. So basically, it's like I give all the distances. So remember, I have the entire graph with me. I can process it any way I like. Okay. Now, this single source shortest path, what is the greediness that I use? What I maintain two sets of vertices. One is discovered set of vertices, and another is non-discovered set of vertices. So what I do is, for that, I maintain a data structure which is known as a priority queue. Okay, priority queue. What is a priority queue? You may have learned in the CS 203. Okay, but if someone is not familiar, then please get familiar with what is a priority queue. In a single line, I can say that priority queue is something like every element that is inserted in a queue has a priority. Basically, it's not just a FIFO queue, first in first out. It's something based on priority. Every element has a value or priority, and the priority, smallest priority value comes ahead, or he takes earlier places in the queue. Okay? So here, what is the priority? It is the shortest distance from the source. Okay, that is the priority value. So what I do is I put the shortest. So initially with these things, I put the elements with the. So initially everything is unvisited. Okay. So what I do, I make S to be visited and just put it in the priority queue. So initially the element S is in the priority queue and the priority value is 0. Okay, put the value here. Then what I do is I extract this S, okay, because this is the minimum value I have visited. So I extract this S, okay. So nothing remains in the priority queue. Okay, the next step, the priority queue is empty. And then what I do is I augment or change the effective distances. Okay, I think I missed one weight. So let's say this weight B2. So I augment the weights of these edges. So this was infinity, this was infinity. So Now I can see if the distance is 0, I can reach from here by traversing a 5. So effective distance is 0 plus 5. So I erase this infinity. I erase this infinity and I make it as a 5. Okay, this distance is 5. I put a 5 here. Quite similarly, from this 0, I am reachable here. And what I do, and I put this node, I put this node. This is node. Let's say we need to give some names. So instead of giving names, I'm just putting the values actually. So I have put the values 5 here. You actually need to put the name and the vertex in the priority queue. Okay. And then I remove this thing and I put a 4 here. So among all the neighborhood, I actually augment, I change the infinity values to some realistic values through which I can reach 4 and 5. And I put this 4 here. But see what happens as soon as I do that, see, these are all the nodes that are reachable from S. Okay, and I have extracted S. So now this is the state of the priority queue, 5 and 4. But since this node, the priority value is the shortest distance from the source, this priority queue itself will change into 4, 5. Because 4 is the smallest, it will come like that. Then what I will do, I will extract this 4 element. Okay, this 4 element I have, and this is already visited, so I just mark it. This has been visited, so that it is not visited again. So I then extract out this 4. Okay, I then extract out this node which has distance 4. So this I make this visited now. Now from 4, I try to augment the distances. If I can decrease the distance. So from this node has a level of 5. Okay, so if I try to up this level, so if I try this path, this is 4 plus 2, 6. 6 is higher than 5, so I cannot minimize its effective distance from the source. Okay, so yeah, I'll keep it as it is. Then what are the other connections? From this node, I am connected to this node and this node. Here the distances are infinity. So definitely I can change it. So this is 4, this is 2, 6. So I will remove this to 6. And what I'll do, I'll put 6 in this priority queue. This is 4, this is 1, so 5, this is infinity. So I'll make this to be 5. So I'll make this 5. Okay. And I'll put this 5 here. Now I see, you see, this is the trick. I mean, 2 elements are at a distance of 5 from each other. Okay, from the source. So which 5 I take? So I need to give some name. Let's say this is A, B, C, D, something like that. So this I just subscript as this is due to A, this 5 is due to D. Okay, and this 6 is of course due to this B. Okay, now I'm done. So now this 2 are visited. Now in the priority queue, you see 5, 6, 5. So what it will rearrange itself as 5A, 5D, 6B. Or it can rearrange itself as 5B, 5D, and 5A. I mean, anything is okay because their priorities are same. The distance from the source S is same. So anybody you can you can do, but we keep it as 5A because A was explored first. Okay. Next time I extract the mean, so I just remove this from this list. Okay, so this I make visited. From this, can I make some changes in the distance, current distances of these nodes? From this, it is seen that this is already visited. It has 2 neighbors out of, I mean, these 2 neighbors are already visited, so it will not change. it tries to update the distance of B, and it sees that 5 plus 3 is 8. Its current distance is 6, so it's better not to update. So it will not update, and it has no more neighbors. So now this becomes permanent. Then this 5D is extracted from this priority queue. So this I make permanently visited. And then from this 5D node, I try to update the distances of unvisited neighbors. So unvisited neighbors are this B and this T. So it is at a distance 5. So this will make 7 plus 5, 12. Its current distance is 6. So better not to update. So, and here the distance is infinity. So current distance is 5. 5 plus 7, 12. So what it does, it just erases this infinity and makes it 12. Makes it 12. That's it. Okay. And at the same time, it inserts this 12 along with the node T in the priority queue. Okay. Now, you see in the priority queue, there are two values, 6 and 12. So 6 is, of course, smaller. So 6 is taken out. The min value is taken out. And from 6, I make this visited. And from 6, I try to update the distance of unvisited neighbors. So it has one neighbor, 12, T, that is unvisited, and currently at a distance of 12. And this B is at a distance 6. So 6 plus 1, that is 7. 7 is definitely smaller than 12. So this updates this distance to 7. Now, since 7, this it inserts. So, but this is already in the priority queue. So this is actually cut off. This is actually taken out. Okay. So its distance is set to be 7. This is already inserted. So now what do you have? You have already only this 7 in the priority queue. You extract out 7. Okay, this T node you extract out and make that visited. And what happens? It has every neighbor visited. And the priority queue is also empty. So this solves the problem. So now I just want to create a tree. So from 0, this is the 5. So it is now, what is this distance? So this is the distance. Now, how it reached 6? It not because of this, it because of this 4 plus 2. So I make this line. Then this became 5. How it became 5? This is 4 plus 1. And then how it became 7? I make this one. Okay. So this is some kind of highlighting I do, and this creates a tree. If you look at the double lines, this creates a tree rooted at this node S. Okay, this is a tree, and now if you look at any node in the original graph, okay, you can easily say the shortest path from S to that node is given by that. If you just follow that tree, you will get that shortest path. Okay, so S to T, what is the shortest path now? This is a distance at distance 7, and the path is like this. Follow this, S to C, C to B, and then B to T, something like that. And the path cost is 4 plus 2, 6, 6 plus 1, 7. Okay, what is the shortest path from S to D? It is 5. So you follow S to C, 4, and then C to D, that is 1. Okay, so this tree, you must remember that a tree is a graph which has no cycle and every node is reachable. So if you look at the double line, it is a tree rooted at S, and I mean any node is reachable from S, and there is no cycle. Cycle following the double lines. Okay. So this tree generated by Dijkstra's algorithm is known as the shortest path tree. Okay, shortest path tree. Okay, so now I hope you understand the execution of Dijkstra's algorithm. So if you just want to know what will be the pseudocode, so pseudocode will be like this. You first initialize all the uh, all the nodes distance to be infinity except the source vertex, and let S be the set of explode nodes. Okay, and so initially S is actually the the start vertex only. The rest are all unexplored. Okay, and while S is not the entire set of vertices, when all nodes are not explored, what you do, you actually select, you actually take out the node which has the mean distance from the source. So initially S is the only node, its mean distance from the source is itself 0. So you take out from this and then try to update the distance of all its neighbors. Okay, and then after that you insert all of them into the priority queue. Okay, so that next time you can extract with the mean distance node at the minimum distance. So remember here, I mean, this priority queue is a very important and essential data structure with respect to this Dijkstra's single source shortest path uh, algorithm. And there are different versions of the priority queue. Okay, like you can use a heap-based priority queue. You can use different kinds of heaps. Okay, one is known as the Fibonacci heap. One is normal heap you can use, and that on that the complexity of the algorithm slightly changes. Okay, so now one thing that we must understand is why this algorithm is successful in uh, in generating the shortest path. Why this algorithm is successful? So to do that, we try to understand one theorem, okay, which is very crucial for this algorithm. So let me just write the theorem. Okay, so this is the uh, lemma that is crucial for our understanding. What is the lemma? It says that consider S, capital S, it's the set of explode node at any instant of time, okay, during the execution of the algorithm, at any instant. Okay, this at any instant. Okay, So if you see this algorithm, this is eventually all become explode. But if you consider at any point, initially this S was only this explode, then it became like this, then it became like this, and then it became like this, and then it became like this, and then 7. So these are as if I create a two partition kind of thing of the graph, where S is the set of explored nodes and remaining is V minus S is the set of unexplored nodes. And what is the claim? Claim is for any vertex U in S, the path PU. What is PU? PU is the shortest S to T, S to U path. That means in this S, and let's say I make a partition. This is my capital, this is my smallest, I should say. This is my smallest, and this is my partition S. This side is V minus S. So whatever vertex I take in this region, let's say this is U, I may have a path to U. That path must be the shortest from S to U. Okay. So how do I prove that? Okay. So what we do is we prove by induction. We prove by induction. And so initially, what is this S? So initially, we prove this by induction on the size proof by induction on size of S. That is modulo S. On the size of S. So, so when size of S is equal to 1, what is it? The vertex is smallest itself, and it is at a distance 0 to itself. Okay, S has no other node, right? Capital S has no other node, only the source vertex. So definitely for each U in capital S, the path P is the shortest from S to T, S to U. So what is the vertex in capital S? That is U, S, smallest itself, and distance to itself is 0. And there cannot be any shorter because that is itself. Okay, so this is true for S equal to 1. Now, let us assume that this kind of partition at any intermediate state, and there are, I mean, after, let's say, S has k nodes. Okay, in this region there are k nodes, and so in this region how many nodes? N minus k nodes. Okay, so V minus S. Okay, that is essentially N minus k, because we assume that the vertex set has n nodes and S has already k, so these are n minus k nodes. Okay, so and I assume that all these distances, I mean, take any two nodes, the distance is shortest. Okay, now what I do is we grow this S to k plus 1. Okay, there may be some nodes here. Okay, we grow S to k plus 1 by adding one node V. Okay, by adding one node V. Okay, by adding V. Now, where do I add V? I mean, see, there's so many nodes here, n minus k nodes, and I can have this one, and so on. So which one I add? If you remember the logic, so So these are explored nodes. Okay, these are explored. So I do not take the explored node. What do I take? I take the one in this region which has the smallest, which has the smallest distance from these nodes. Okay, I take the mean value from the priority queue, and let's say this is the node. This is the node, and it was connected to this node. It was connected to this node, and there was maybe some path to this node. So these are all connected. Let's say this is the thing, and my partition just becomes like this. Okay? It increases to 1. What I need to show is that any two node, I mean any node inside this S, my modified S, that is S prime now, because I have included V in this partition. Okay, and this is my new partition. So what I want to prove, I want to prove that this for S is now K plus 1, right? Now I have to just show, take any two nodes, any node U inside this S prime, its distance from the smallest is also the shortest. Okay. So of course, I don't have anything to prove for nodes other than this new V. Okay. I don't have anything to prove because they are already by inductive step, they're already shortest. So now I just need to uh, claim that small s to u, smallest to v basically, is shortest path. Okay, that is PV. So how to argue that? The argument is that, see, I connected this to here. Okay, I possibly could have connected it through here also. I could have possibly connected it through here also. It depends on the number of connections V has through any of the members of S. Okay, any of the members of S. Okay, so let's say, let us contradict ourselves that this is this through another node. So this, let's say this is U prime, this is U double prime. Let's say this is not the shortest. Let's say this is the shortest. So if this were the shortest, because this S to U prime, U double prime is already shortest, S to U prime is already shortest. Okay. Now, why if you remember why I why I chose this view according to the algorithm, this is because, let's say, distance of U prime plus, let's say, cost of U prime comma V, that must have been less or equal to distance of U double prime plus cost of U double prime comma V. Okay, this is the logic. This must have been smaller than this for all of them, for any such case. Okay, okay. So therefore, it must be the case that the new, I mean the new V, because if that is not the case, if this U prime would have U double prime would have resulted a better path, then probably it would have been the other way around. It would have been this way. It would have been, this is the case. And I would have, due to the priority queue mechanism, I would have extracted this U double prime. And I would have connected U double prime, but actually I have connected to U prime. This is because this. Okay. So that means there is no other path from smallest to V till this time. Okay, till this time. Okay, that results a shorter distance to V from smallest. Okay, so this concludes the proof that. So now, I mean, this step is okay. I mean, for S, when S is equal to K plus 1 also, PU is shortest. I can claim. Okay. So therefore, I mean, this is true. Therefore, by induction, this is true for all K. Okay, all K up to say N. Okay. So this is how we prove that when the algorithm terminates, S is equal to V, basically. So that means from PU is shortest for all. PU means actually it is smallest to U, shortest path. Smallest to U. Okay. So now,
hello.
so my request will be
Hello.
to hello.
आकाश देख रहे हो? ये कौन सा प्रॉब्लम करवा रहा है ये? क्या क्या क्या?
Please make your sound off. Okay. So now, one fundamental question that is often asked, that so one thing we need to prove that the algorithm terminates. Number two, on termination, PU is shortest for all U in V. Okay, so these are the two things we need to prove. This second part we proved. The first part is easy to show that, okay, eventually S will become equal to V and then only the algorithm terminates. Easy to argue from the algorithm. One important thing that is often asked is we assume that all weights, the weight is WUV. Okay, so when UV is an edge, okay, when UV is an edge, we assume that this is non-negative. Okay, this is non-negative. So a natural question arises is what happens if some weight UV is actually negative? What happens in this case? Okay. So the answer to this question is even for a single edge E such that WE is less than 0, which has negative weight, the algorithm may fail. The algorithm may fail. So what do you mean by the algorithm may fail? The algorithm will terminate, but it will fail to generate the shortest path. It will fail to generate the shortest path. Okay, you can actually explore a counter example. Okay, remember the counterexample has to be properly designed, that the algorithm is working. I mean, the algorithm is starting and eventually it is stopping. But when you look at the shortest distances, then you will see that the algorithm has returned one path to be the shortest path. But actually, it is incorrect. I mean, you will manually find that there is another path which is actually the shortest, but somehow the algorithm is not returning the shortest. Okay, so this is the uh, what is this? So this is the uh, reason people say that Dijkstra's algorithm may not work. See, this word is used, may not work. It is not said that it must not work or it does not work. Okay. Most likely, if you are intelligent enough to generate a proper counterexample, so there may be one or two cases when this Dijkstra's algorithm fails, if at least one edge has negative weight. Okay, so that's why, since there is a counterexample, and who knows whether the input graph may or may not have a counterexample. So, I mean, it is generally stated that Dijkstra's algorithm does not work for negative edges, edge weights. When the edge weight is negative, it does not work. Okay, because I mean, one can always design some sort of counterexample where it will fail to give the shortest path. Remember, it is not the algorithm will fail. I mean, algorithm will terminate. It will give some path, but it will not be the shortest. The desired result will not be produced. Okay, so that is the thing. Now, a natural question is, okay, if one such edge has a negative weight, then if Dijkstra's fails, then what is the solution? Okay, so I will just name the solution, but I will not explore here because that is something, a different algorithm design paradigm known as dynamic programming. When we will deal with that, we will solve that. So that algorithm is called Billman board algorithm. Okay, so this algorithm is used when there is negative weight edge in the graph. Okay, and this algorithm successfully solves the problem. Okay, but at this point we will not discuss it. This is something in the dynamic programming. Okay, so now we have a couple of minutes left. Okay, so yeah, I will rather stop here. If you have any questions, I will take up. Okay. If any questions. So quite similar manner, we can solve something known as a different problem. See, these are all greedy choice that we are making. Another problem that is often solved using greedy, which is called the MST problem. What this MST stands for? Minimum spanning tree. Okay. Just in one line, we can say this problem, that given a graph G, which is V comma E, set of vertices, it's a connected graph, assume. Okay, the job of the minimum spanning tree problem is to find a subgraph, okay, subgraph G prime, which is same set of vertices will be there, but a subset of edges will be there, E prime, okay, where E prime is a subset of E, such that you take up the sum of the weights, okay, in this edge set that you have taken, that is minimum. That is minimum. So you can actually potentially take many subsets like E prime. You can take many subsets, E prime, E double prime, E triple prime, and so on. Many things you can take. But not everyone will minimize this term. Okay? Only a few of them may minimize this term. What is this? This is the sum of the weight of the edges is minimized. And remember, the vertex set is remaining the same. I do not change the vertex set. One may make a mistake that, okay, I will run Dijkstra's single source shortest path to do the problem. Probably, see, this is the kind of structure that was generated by the Dijkstra's. Now, if I try to, I'm erasing something here. Let's say, this is the situation. So what I will do, I will just put a cross. So I will just take this edge, and this edge, take this edge. No, I will not take that edge. So by taking these three edges, I have connected these 4 nodes, and I just need to connect these 2. Okay, so what I can take this edge, and I can take this edge. Okay, so see, there is a difference between the, so here the sum is actually 2 plus 2 plus 1, 5, 5 plus 1, 6, 6 plus 4, 10. So the MST has a weight of 10, whereas if you had chosen the single source shortest path tree, that SPT, then that would have a weight of 5 plus 4, 9, 9 plus 2, 11 plus 1, 12, 12 plus 1, 13. Okay. So shortest path tree would have a weight of 13, whereas the minimum spanning tree has a weight of 10. Okay, so this is better. So that means SPT is not a minimum spanning tree. That is the main thing I wanted to highlight, that SPT, that is the shortest path tree that is generated by Dijkstra's algorithm, is not the MST. So Dijkstra's algorithm will not work here. Okay, so we need to think of something different. Okay? We need to think of something different. So this is the problem, minimum spanning tree problem. So hope I have been able to motivate you about the problem. So how to solve it? I leave it for today, and we'll take up the MST problem in the next class. In the meantime, I will send. Let me make an announcement. I mean, is today is 25th of January. So 25th of January. On next Sunday, that is the last day of this month, I will take a quiz actually on whatever has been the topic. I mean, not including this shortest path tree or time ST. It will be up to the interval scheduling problem, various interval scheduling problems that we have taken, and uh, matching problem. Okay, so these couple of things we will have a MCQ type quiz. Okay, so I will send a mail to all of you. I mean the modalities.
Sir,
Uh,
sir, can you
so-
take it on Monday, please?
no, Sunday is a good time, I think.
We already have some issues related to homes actually. We have already, shifted everything to Saturdays and Sundays. Due to the course work. So if it is possible, it will be better, sir, if it's on
No,
Monday.
what is the problem? If you alone have problem, I mean,
So
what
I
is the
think
problem?
many people will have problems, sir, I guess.
No, no, no. What is the problem? I just want to know.
Sir,
I do not,
actually, I need
I
to
do not
take
want
my
to
parents
waste.
to doctor's chamber, sir. They are actually weak. They are being through their post-COVID patients, sir. That's why I've taken an appointment on Sunday.
Oh, Sunday, but then make it 30th then, because I want to
Okay,
do it this month. Hmm.